So today we'll talk about max cut. Right? Max cut is a computational problem on a graph. I'll describe what it is, and then I'll say a few words about why we care about solving such problems in the context of learning and data science and so on. Okay, so the problem is the following. Let G be a graph. Right, let's say it could be weighted or unweighted, doesn't really matter. Could have vertices and edges, or could have, of course, vertices, edges, and weights. Right? Nothing really changes when the graph is weighted in this context. Right, and the goal, so the goal of maximum cut, right, is to find to split the graph, the vertices of the graph in two, as to cut the maximum number of edges in between. Right, so max of subset of the vertices of the cut, right? So here it's sort of the opposite of what we were doing before, because here we want, right, to split the graph, and we want the number of edges in between to be maximized, maximum cut possible. Right? Well, before we were doing things like minimizing the cut, right? But minimizing the cut had the problem that, right, they had that issue that it was sort of easy to cheat, right? Because we could just take the minimum cut could just be obtained by taking nothing on one of the clusters and everything on the other one. And so the maximum cut doesn't have this way to cheat, right? Say the complete graph, for example, the best way to cut it is just to, put half on each side. This is how you get the most things in between. And in general, we'll see that maximum cut will be roughly balanced. So we don't have to do this balancing that we had to do when trying to do clustering and minimize and minimum cut and so on. And if you think about it, something like minimum bisection is not so different from maximum bisection, right? Because doing minimum bisection is roughly the same as doing maximum bisection of the complement, right? And with the constraint that things need to be balanced, this ends up being exactly the same problem. And so here, while from the viewpoint of data science, learning, and so on, it's hard to justify why would one maximize the cut, even though this has application. The type of intuition one gets from studying this problem is actually super, super useful. And this problem has sort of less issues with normalizing and so on. And the algorithms that we're going to develop in this context are going to be super, super useful for clustering and for actually many, many other things. Okay, so we're going to focus now on this problem. Now, unfortunately, this problem is known to be NP hard, right, or NP complete. So what does this know? So what does this mean? This means that this problem, if this problem is just as hard or is harder or just as hard as any problem in NP. Okay, so this is not a course in complexity, so I'll be brief, but basically problems in NP are problems that are hard to solve, but they're easy to check solutions of, right? So usually problems are not, in computer science, are not defined as maximizing something. They're defined as, is the maximum of something bigger than something else, or there exists a set S for which the cut is bigger than 50, right? That's usually how they're formulated. And although this problem is hard to answer, right, because answering questions of that type is essentially the same as maximizing. Because if you can answer questions like that, you can just try for 50, for 49, for 51, and so on and so forth. You can even do better. You can do some kind of binary search, and you would be able to find the answer. Right? But if I want to convince you that there is a cut of size 50, it's very easy. If I have a cut, it's very easy for you to check that it does work. Right? And this is essentially what a problem in NP is. And what NP hardness means that if you have an algorithm that is able to solve this for all graphs, then this algorithm can be transformed into solving any problem in NP, right, via reduction. So it might now take longer, or it might take a lot longer potentially, but if it's polynomial, if it's a polynomial time algorithm for max cut, it will still be a polynomial time algorithm for the other problems. Right? In fact, this problem itself is also NP, so it's actually NP complete. Right, this is the really, really, really nice story of NP hardness and computational complexity, that essentially all the problems in NP or all these a huge set of problems in NP are actually exactly the same hardness. Unfortunately, we can't actually show that they are difficult. Right, this is the big question of P equal or different than NP, right, which is, it could be that actually all these problems are just as hard as one another, but they're actually all easy. Right? This is not what we believe. But this is still a big open problem that if you solve, you get $1 million and you become very, very famous. And But it's widely believed that they are different, which means that there is no polynomial algorithm to solve this problem. Okay, so I mean, we've seen these things before, right? Where if we wanted to minimize like the normalized cut and the ratio cut and all these things, we believe there was no algorithm that could do it all. Yeah. So now you can take two perspectives, right? And in this course, we're going to take mostly the perspective of, well, we don't want to solve every single graph. We just want to solve graphs that come from data. We don't care if, you know, if our algorithm doesn't work on every single graph. We just want it to work on most graphs. And this may be a different requirement, where most needs to be defined in some way, of course. Now, for this lecture, I'm going to take a slightly different perspective, and this turns out to be a super useful perspective for data science and learning and mathematical signal processing, because it motivates very, very nice algorithms that we're going to be able to use for our purpose. Right? And it's the point of view of approximation, right? So this isn't too hard, but we can ask the question of finding approximation algorithms. Right, so the idea is, can we find an algorithm that, yeah, maybe doesn't compute the maximum cut, but always computes a cut that we know is at least, say, as good as 90% of the maximum cut. Right, so this is the question. And this is what we're going to talk about today. We're going to talk about approximation algorithms and a very, very elegant approximation algorithm from X-cut to Gumans and Williamson in 1995, so around 35 years ago. Okay, so let me start by giving you a very, very simple approximation algorithm. Right, that already gives something non-trivial. And it's the following. Let's take a greedy algorithm. So let's take Okay. Here's a very, very simple procedure that I'm going to describe that I'll show to you that it already gives an approximation ratio. Okay, so the procedure is the following. Let's order the vertices V1 through Vn. And now let's think of two buckets. Okay, so we have my bucket S and my bucket S complement. Right, so now V1, we put it, say, in S. Now for V2, right, we're going to put it, say, in S complement. Okay. Let's say. Now, if V1 and V2 had an edge, I'm cutting it, otherwise I'm not cutting anything. And now the idea is for each VK, right, when I'm deciding where I'm going to put VK, right, maybe V1, V3, V4, here V2, VK minus 1, right, a bunch of vertices are already done. I'm doing it sequentially one by one. And when I put VK, I have a bunch of edges that are connected here, and a bunch of edges connected to this side. And I just check which one has the most edges. Right, so if I have more edges here than over there, I'm going to move VK to this side. Right, and I just do this every step. And if you think about it, the edges from VK to nodes that are behind VK in this ordering, right? Let's say back node, back degree or back edges, I'm going to cut at least more than half. And at every single step, I get at least more than half of the edges from a node to the ones behind. But now if you see, every edge is going to be counted on this exactly once, right? Because if it's an edge from, say, V10 to V20, then it's not going to be counted on V10, but it will be counted as a back edge for V20. And so effectively, I'm always cutting at least half the edges. Okay? Draw a picture, try to convince you of this. But in this algorithm, just this greedy algorithm has the property that the cut of S greedy is bigger or equal than half, not even of the best cut, but half the number of edges, right? It's very, very easy to cut at least half the edges, okay? But for sure, I mean, there's no way that the maximum cut will be more than the number of edges, because I cannot cut more than the number of edges. So in particular, this is always bigger than the max cut of the graph G. Okay, so here we already have an approximation algorithm of approximation ratio half. Okay? So getting an approximation ratio of half is almost trivial. And in fact, there's even somehow a simpler algorithm, right? Which is, let's do an even simpler procedure than this, which is just a sign, right? Just a sign. So let's call this the random algorithm. lots of algorithms are random. This one is just more random, right? Assign each node to S or S complement at random and independent with probability of half. Right now, if you look at each edge will be cut, right? If you look at edge VK, say V, and let's give an example, right? If you look at edge V7 to V12, right, this edge will be cut exactly with probability half, right? Because there's half probability in the same one or in a different one, right? So each edge is cut with probability 1/2. Of course, they're not independent, but if we're taking the expected value of the size of the cut, that doesn't matter, right? Because expectation is linear, regardless or not if the variables are independent or not. I mean, we've seen this in the course, right? So this means in particular that the expected value of the cut of S, let's call this algorithm random, is bigger or equal than half number of edges, right? And therefore also bigger or equal than half, okay, I should write it on this side, expected value, okay. Expected value of cut of S random is bigger or equal than half of the number of edges, right? So there you go, two different algorithms that give you an approximation ratio already of a half. And now, okay, now we're going to improve over this a half, right? We're going to show you a very, very nice algorithm by Humans and Williamson that improves over this half. And in fact, the number that I'll show you is around 87%, and that one is believed to be optimal. But I should say that now you can define these things in many different ways, right? You can say, well, is it true that, can this be improved? Not over half of the number of edges of the cut, but half of the edges. And it can't, right? Because sometimes max cut really is half of the edges. Just take, or around half of the edges. Take, say, the complete graph, for example. Right, and so now you can do approximation ratios in all sorts of ways, like, oh, what if the maximum cut is half the edges plus a little bit? Can I get at least half the edges plus some other little bit that depends on the difference in the beginning? Right, so like going from maybe the maximum cut is 1/2 plus epsilon, can I get something that's 1/2 plus some function of epsilon? Can I get this function to be as good as possible? Right, there's all sorts of things you can think about, and this is called max cut gain, and there's lots and lots of different forms of approximation. But we're going to be interested in this one, right? This cut of some algorithm compared against the maximum cut. And so I'll show you now a very, very nice algorithm that has a huge impact in mathematical data processing, even though the problem itself doesn't appear to be related to, right? And even the way of defining approximation ratio, right? Like when we're doing learning or data science, our objective value, our objective function doesn't often have a meaning for itself, right? We have some kind of fit to the data and we want to minimize it, but getting half the fit or double the fit doesn't usually have much meaning necessarily, right? We want to approximate the object, not necessarily the fit. And so, I mean, sometimes we might, but when you're like half the fit or something like this could be a terrible point from the viewpoint of learning. But in any case, the algorithms developed for this type of approximation will be extremely useful, as we'll see. Just like how we did for when we're looking at spectral clustering and so on, we're going to reformulate the problem of max cut in sort of a more linear algebra way, right? So let's see. So what we had was we wanted the maximum, right? S is a subset of the vertices, right, of the cut of S. But we can formulate this just like how we did when we're looking at spectral clustering by like a membership vector. Right, we want yi to be, say, 1 if I is in S, and minus 1 otherwise, and if I is not in S. Right, and now we can write this in a different way, right? We want to maximize over all such vectors y that have plus or minus 1s. And what we want to maximize the sum for I smaller than j, right? And now here we can have the weights. Right, because the cut is defined as the sum of the weights of the edges that are cut, if they're weights, otherwise just the sum of them is just the number of edges. Right, and now here we can put 1 minus yi, yj. Right, and a half. Why? Because if if yi and yj are in the same cluster, then this becomes 1. 1 minus 1 is 0, so I get 0. Right? Otherwise, if they are in different clusters, I get a minus 1. So I get 1, right? Plus 1, I get 2. And the 1/2 cancels the 2. So I just have the sum over I and j of wij when they're not the same. Right? And so this problem we'll be focusing on. Of course, we can also write this as a quadratic form on the Laplacian, right? Of course, and we'll see that a bit later. But for now, there's no need to do this. And so we're going to consider relaxation of this problem. And this is the really cool idea, right? Is that before we saw relaxations of this problem in which we had y become now a vector in, instead of a point in the aperture become a point in the sphere, and we're studying those relaxations. Now the idea here will be different, right? And this is what's really cool and what's the key idea. And in a way, it goes back to the work of Blazov-Lobaz and the theta function to do relaxations of things like independence number of a graph and so on. Which is instead of relaxing the vector y going from hypercube to the sphere, we're going to relax in a different way. We're going to make each yi go to a vector vi that's going to live in Rd. Right, so now we're going to have a graded relaxation because, right, the vector, yi lived in R. I mean, it lived in plus or minus 1, but in particular, it lived in R. So we're going to relax to some Rd, and the condition that we had, right, that yi, say, square was equal to 1 in norm, okay, is going to be transformed into the condition that the norm of the vi, I don't need the square, maybe it's just adding extra stuff that's not helping, right, that the spectral norm, that the L2 norm of vi, just the norm as a vector, is 1. Okay, and now products are going to become just inner products. Okay, so let's see what we have. Okay, so in the notes I call this ui, so maybe let me use the same notation, so that it's easier to read. Okay, so what do we have? We're going to have max, right, of now u1 all the way to un in Rd, right, where the norm of each one of them is 1 for all I, right? It seems like a strange thing, but bear with me. Some I smaller than j, or 1/2 wij, 1 minus ui transpose uj. Okay, so this will be the relaxation, right? This will be the value of actual max cut. And this will be the value, let's call this the relaxation index by d. Of the graph. Okay, I don't think we'll actually need that notation. Okay. So now, right, why is this a relaxation? So we want to argue that the search space is bigger. In particular, we'd like to argue that Rd, that G is actually bigger until the max cut. And why is that? That's easy to see, because you can just constrain yourself. If you have in this set, and if you further constrain these points, right? If for these points here, you say uk actually needs to be of the form some number alpha k times, say, e1, right? The vector that has a 1 in the first entry and 0 everywhere else, right? Where this guy is just a real, right? Then you reduce exactly to this problem, right? Because everything is happening just in that first dimension. Right, and so you will have that, the vectors in Rd, but actually they're d-1 coordinates, except the first one are 0. There being norm 1 just says that this alpha k is either plus or minus 1, right? It corresponds exactly to that y. And this inner product becomes just the product between numbers, right? So with this further restriction, this problem becomes exactly equivalent to that one. And so you're effectively searching over a bigger space, right? So this is true for sure. Okay, good. But now the question is, why does this have any usage whatsoever? Right? Why should this be even a good idea? Right? For this to be a good idea, we need two things to happen. Right? We need one. We need that the value of the relaxation of, say, RDG is related, not just that it's bigger, right? I mean, it could be that I have 2 times that, for example. It wouldn't be useful. It's related to the value of max cut, right? And moreover, that we would like that from a solution of RD G, we can get a good solution from Xcode. And two, that RDG is easy to compute, is easy to solve. Right? Otherwise, it's important that this new problem has something to do with the original one, and that it is easy to solve. Right? We saw in the spectral clustering case, this was roughly this happened, right? So we had that the relaxation over the sphere was much easier to solve because it was just a spectral problem, and that the value was somehow related, right? This is what Shiger inequality gave us. And so this is now what we're going to do. We're going to argue. I'm going to start by arguing why is it that it's easy to solve, and then we'll move from there to showing why it is related and how we can build solutions to the original problem from